Thank you, Zoom. All right, so this is a problem from our book. It came up a few different times in the book, and it's about whether your facial expression, your demeanor, if you appear to be smiling versus if you have a neutral expression. Is a judge going to be more lenient on you if you're smiling than not? So we have a sample of 34 people who smiled during their hearing and 34 people who kept a neutral expression. So these are two different groups of people. So this is that part of that independent population I was mentioning. The values are a measure of how lenient the judges were. And so here I don't have the data right now, I just have all the summary statistics. And really that's all we need to make a confidence interval. We need the sample stat, which are the means, and we need the sample sizes, and we need the sample standard deviations. So we have everything we need to use those formulas. So the smiling group had a mean of about 4.9118, with a standard deviation of about 1.609. The neutral group had a mean of 4.1176. It's a little lower leniency rating, so it seems like the smiling group, there was more leniency with them. But they're both around 4-ish. Are they really that far apart? That's what we're going to answer next with a hypothesis test. But for now, we're going to find a confidence interval on this difference, and we have the standard deviation. So the only thing we don't have here is we need to find the correct t-score to go with a 96% confidence interval. Otherwise, all the data we need here is provided. And then if you do find resources outside of this class for a difference in means, there are other ways to calculate the degrees of freedom. There's this really crazy formula. It's a humongous square root thing. We're just going to use this simple method of the smaller sample size minus 1. Here they're the same sample size, so it's no big whoop. Okay, so I'm just going to draw a little picture to help set this up for the confidence interval. Because I got to find my t-score. I want 96% in the middle. So alpha would be 1 minus 0.96. So that leaves 4% for the tails. So alpha over 2 is that 4% cut in half. So each tail gets 2%. And I need to know that to get the right t-score to use in my formula. The confidence interval formula, remember, right here, is take the sample statistic, which is the difference in the given means. It's supposed to be a 2 there. Plus or minus the magic t-score we have to calculate times the standard error, which is that funky square root. And so I'm just going to start by writing some things down, but then I'm just going to go to the spreadsheet. That T star right there on a spreadsheet is the T inverse. Tail probability helps me figure out what number that is there. So 0.02 would be my alpha over 2. And degrees of freedom is the smaller n minus 1. They're both 34. 34 minus 1 is 33. So that's how I'm going to calculate the t-score in just a minute. This is going to give me a negative number because t-score middle is 0, negative to the left. So I'm just going to take the opposite of that when I do my formula. So we're just going to go to a spreadsheet, enter these numbers, and hope. So let's see, desktop. Did I restart this one to mean confidence interval? And that is not it. How about this one here? That is not it either. Okay, so we're just going to revise this one right here. This is like one of your homework problems. I'm just going to leave that, make a copy. So this is, what are we doing? To mean CI. How about that for a name? So we've got to put in our smiling versus our neutral. And And sample size, we just got to type all this stuff in, 34, 4, and our means were 4.9 something. Let's get that here.
118.
Oh, you have got it written down.
I do.
See it. Ooh, why did I type 34? Whoa, what just happened there? That was bizarre. What was it, 118?
Yeah.
Okay, and then the standard deviation.
809.
809, thank you. And this one was what, 4.1?
1176.
1176, thank you very much. And 229. And I don't know why I repeated the confidence level. I must have been messing around with something there. 0.6, I'll figure that out in a minute. Okay, so the X bar D, that's just the difference in these two. So if I go to that cell there, and in case you're new to this Zoom meeting, I'll reshare this so you can get on this sheet. Share. Those of you looking at this on YouTube, the link should be in the description of the video. All right, so then, oh, I did put the complicated degrees of freedom in here. I was just messing around. It's a crazy formula. I'm not going to go over it, but I put it in here just for fun. The simple one, I say just grab the minimum of the sample sizes above and then subtract 1. So the computer looks up there for me and says, okay, which one's smaller? Grab it and then take away 1. So I have the simple version there. So this is what we're going to do over here. I'll highlight that in blue.
Probably put it in there because the book does give one example where they ask us to kind of compare what it looks like with the they don't really give you the complicated formula, but they tell you that this is how they figured it.
Okay. Yeah, and typically I would say, I don't know, in statistics textbooks, statistics videos, like 80% of the time, teachers will use the more complicated formula than the simple one. And there's a couple other versions on the simple one. Standard error here, let's see, that is that formula. So I'm using the standard error. It doesn't depend on the degrees of freedom here. That is where I take the square of the standard deviation from one sample divided by the sample size, add that to the square of the other standard deviation divided by its sample size. All that's inside a square root. So there's my standard error. The t-score I want right here is from the simple version of the degrees of freedom. And so that's where I'm using that opposite of the t inverse. Inside the formula here, I did the 1 minus the confidence level divided by 2. Notice I had to use parentheses to get that to happen right. Order operations matters. And then I grab the degrees of freedom in the simple version. And notice it is a slightly different t-score, 2.09-ish, 2.138. They're not too far off. Margin of error, remember margin of error is the t-score times the standard error. So that one's pretty straightforward. And then to get the lower and the upper, we just add and subtract this from our difference in means up here. And so that's pretty straightforward here too. Just take the difference in means, subtract the margin of error, difference in means plus the margin of error there. And a spreadsheet really is the most efficient way to do this because the spreadsheet deals with a whole lot of decimal places, so I don't have to worry about rounding to the end. So then if I'm asked for this to 4 decimal places, I just highlight them and say, okay, take that down to 4 decimal places, computer. 1, 2, 3, 4. And so then I get a more accurate version here. So I'm getting a confidence interval of negative 0.0357, 1 point, I'm just going to bring this over so I can write it down. So after the spreadsheet calculation, we're getting confidence interval, 96% confidence interval. of negative 0.0375 to 1.6259. So that's one way, right? This is my lower estimate on the difference in the means, and this one is my upper. Sometimes in literature, when you read about confidence intervals, what they often give, instead of the range, they'll give the midpoint, right? The actual difference. So that would be the sample stat. And then either next to it, like in parentheses, or maybe they'll do a plus or minus the margin of error. So our difference was 0.7942 with a margin of error of 0.8317. And a lot of times when I look up reports on confidence intervals, they'll often state what the middle of the confidence interval was. They're saying, hey, we think the difference in the populations is this, and that'll be in parentheses next to that. So sometimes you'll see that the 96%, let's see how they word it, 96% difference in means. And they would just say it is 0.7942, and then in parentheses, they would have the margin of error, 0.8317. It's kind of a standard way they'd have it in papers. All right, so next thing, what does that mean here? So we have the smiling group and we have the neutral group. So, and we took smiling minus neutral, so that's important. So this number right here is the average for the leniency for the smiling minus the average leniency for the neutral group. And it is positive, which implies that mu s might be greater than the average leniency for neutral. But something to note here in this interval, right, if we draw it out on a number line, negative 0.0375 could be 1.6259. 0 is in this interval. So could it be that there's no difference? The answer is, according to my confidence interval, yeah, there could be no difference. They could be equal. Not really sure. So we think the average difference in leniency is somewhere between negative 0.0375 and positive 1.659. So let's write that down. So confidence interval interpretation. So we are 96% confident that the difference in the average leniency right, so I have to go back to what my samples and populations are. Average leniency of people who smile compared to people with a neutral expression. Add something there to make sure I get the order right. Smile minus neutral is between negative 0.0375 and 1.6259. That's it. zeros in that interval. So there might not be a difference in leniency whether you're smiling or not. So that's when we use a hypothesis to check that part. So we have some evidence, but we don't have a p-value, so we don't have a complete answer. So let's do a hypothesis test next.